Now that we're talking about graphing log functions, it probably won't be a big surprise that we're going to graph them in a very similar way to how we graphed exponential functions, because after all, everything else with logs and exponents is more or less the same, or the flip version, or a very related version of the same processes. So let's just start by getting the general shape of a log graph, the simplest one, the parent graph here, y equals log of x. And we'll just kind of make one of our usual XY charts here. And for reasons that you'll see in a second, I'm actually going to put the y's in first. It'll just be easier to construct it this way. So remember, when we have just log of something, that means log base 10. I'll put that here just so we can see it. And so what we're really saying is to find x, like this is the same as saying x is 10 to the y. And so 10 to the negative 2 is 1/100th. In other words, log base 10 of 1/100th. 10 to the something is 1/100th. That thing is negative 2. And this pattern is just going to continue by powers of 10. You can see this is going to be a little bit funny to graph, but let's see what we can come up with here. Actually, I'm going to move this all just a little bit to the side. We might need some room. Okay. Well, it's going to be hard to graph x equals 1/100th. I'll at least put up some little hash marks for the y's. So when x is, basically right here, y is negative 2. When x is still basically right there, y is negative 1. When x is 1, y is 0. When x is 10, I'm not going to go too far over, and then I'll go sort of as far over as I can here. So a little bit off scale, but we've got the general idea that the graph is going to start over by the y-axis and look something like this. And just as we had an asymptote when we were doing exponential graphs, we also have an asymptote here, except this time we can see it. It's the y-axis. So I'll just note that here. Asymptote at, sorry, it's the y-axis, but it's x equals 0. Okay. And I think what's important to note here is that really the two main points, if we wanted to graph this without making a whole table, points we would look at are 1, 0 and 10, 1. And if we want to sort of make these more general, this would actually always be 1, 0, even if we had a different base. And this would be base, comma, 1. Why is that? Well, because if we had log base b of b, that's always going to give us 1 regardless of what that is. So these points should look kind of familiar because they're just the flip of what we had when we were graphing exponential graphs. So just as a quick review on that, when we were graphing y equals 2 to the x, we said our main points were that when x was 0, y is 1, and when x was 1, y was 2. In other words, we'd have 0, 1, and 1 comma whatever the base was. Well, look at this. We've got same thing, just backwards. So same general idea. And this is what I mean. Pretty much everything that we do with logs is either the same thing or like the flip version, but very much related to how we did it with exponents. Okay, so let's do one more simple graph over here, and then we'll start on some ones with transformations. So y equals log base 3 of x specifically. And in fact, let's take what we learned here, that we're going to have 2 points. We're going to have 1, 0, and we're going to have base, in this case 3, comma 1. And we could check these points, right? If we put in x log base 3 of 1, so the exponent that turns 3 into 1 is 0. And then log base 3 of 3, the exponent that turns 3 into 3 is 1. Okay, so these points work. So I'll put them in here. we have when x is 1, y is 0. When x is 3, y is 1. We know that we're always going to have that asymptote on the y-axis at x equals 0. Draw that in there. And so we know that this graph is going to start along that axis, go up, kind of curve down that way. And that would be our graph of y equals log base 3 of x. So let's move on to a little bit more complex one where we now have horizontal and vertical transformations. And I'll just put in here, these are the transformations. It goes 3 to the right and 1 up. And so the first thing that I will do is I'm going to put in the vertical asymptote here. 3 to the right, so vertical asymptote at x equals 3, and I'll label that. Again, that would probably be a dotted line if you were doing it, but not a big deal. Okay, when we were graphing exponential functions, we were looking for places where the exponent equaled 0 and where the exponent equals 1. Those are kind of our two main points that we would use to shape the graph. And logs are exponents, and so we're really doing the same thing here. Let's focus on just this part for now. So we want 2 points that work out nicely, of course. And the problem here is if we just put in a random number for x, like, x equals 10, well, then we'd have log base 2 of 10 minus 3, log base 2 of 7. We can't, like 2 to the something equals 7. It just doesn't work. Like we could do it with a calculator, but it would be kind of messy. So we need numbers that actually work. Here's kind of the shortcut or the technique really to figure out what works. We want, and I'll just focus on this part right here. We want basically the points where log base 2 of something equals 0 and where log base 2 of something equals 1. Because logs are exponents, so we want the exponent to be 0, we want that point, and we want the point where the exponent is 1. And so we could actually just put these in exponent format and solve these. So that would be 1 equals x minus 3, and therefore x equals 4. And we can have 2 to the 1 equals x minus 3, 2 equals x minus 3, and therefore x equals 5. And so the way of thinking of this is if you have log base 2, you want the places where this thing is 2 to the 0 power, and then where this thing is 2 to the first power. If we had, I'll just come over here and make up a random one. If you had that, you'd want where this thing equals 7 to the 0 power. And then you'd want where this thing equals 7 to the first power. So those are the 2 points that we're looking for. And that's how to find the x values that we actually care about, is whatever you're taking the log of, set that equal to the base to the 0 power, which will just be 1, and then set that equal to base to the first power, which will just be whatever the base is. So that's the technique for finding the points that we're interested in. So let's see what values we actually get from that. And I'll erase this just for a little room here. When we have, coming back here, when we have x equals 4, all right, so this is going to be, I'll write this out just to be safe. So it'll be log base 2 of 4 minus 3 plus 1. Remember, this is 0 because we made it that way on purpose. 2 to the 0 power is 1. Okay, so that gives us our first point. When x is 4, y is 1. Then I'll put that on here. When x is 4, y is 1. And then let me do our second point. I'll do that over here. So that's when x equals 5. So we have log base 2 of 2 plus 1. This is 1. We made it that way on purpose. So 1 plus 1 equals 2. And we have this point 5, 2. So I'll put that on there. And now we can graph, again, knowing the general shape of a logarithmic graph. So we'll start low, stay along the asymptote, and then curve through those 2 points. So that's this graph. And it started with finding the values of x such that log base 2 of something equaled 0, and then log base 2 of something equaled 1. And if you wanted a third point, just to make sure, so we had log base 2 of x minus 3 equals 0, equals 1. So another point we could put in would be log base 2 of x minus 3 equals 2. Okay, so that would be 2 squared. So I'll just put this in exponential format. So 4 equals x minus 3, x equals 7. And then we could plug that back in. Well, let's do it. Let's see what we get. Log base 2, 7 minus 3 plus 1. Log base 2 of 4 plus 1. We made this equal 2 on purpose. Okay, so when x is 7, y is 3. So that's 1, 2, 3, 4, 5, 6. Let's say 7's about there. And yeah, pretty good. So we don't need that point if you're comfortable with just the asymptote and 2 points shaping the graph, but we could, of course, use that additional point. So let's do one more of these. And we'll start, as always, we'll label the horizontal shift and the vertical shift. And we'll start by putting in the vertical asymptote. So I will put that in. So that's at x equals -1. Let me make that narrower. Yeah, that's okay. All right, so I'll label that vertical asymptote, x equals -1. So remember, our trick here is that we want x plus 1 equals 5 to the 0 power. And then x plus 1 equals 5 to the first power. So for this one, that's x plus 1 equals 1. So x equals 0, okay. And then x plus 1 equals 5. So x equals 4. Those are the two x values that we're going to use. And you know what? Just I'll put it in. Again, we don't need this, but we could also put in one more point. So x plus 1 equals 25. X equals 24. Now you can kind of see the reason that we really want to be able to shape this off of 2 points is because even like our third point here, x equals 24, we're not really going to graph it all the way over to x equals 24. But it might give us a general idea of which way it's shaped. So let's go back to these 2 points and find our y values. Okay, when x is 0, 3 log base 5, 0 plus 1 minus 4. So 3 log base 5, 1 equals log base, anything of 1 is 0. 3 times that is still 0. And so we end up with -4. So we have our first point when x is 0, y is -4. Then for our second point here where x equals 4, now you could shortcut this a little because we came up with these 2 numbers in order to make the log come out to 0 and in order to make the log come out to 1. So you could kind of shortcut this and know that, yeah, this whole log base 5 of 4 plus 1, it's 1. We made it that way on purpose. We already know what the result is supposed to be. But of course, nothing wrong with just running through the math. Sorry, let me not mix up those. So y equals log base 5 of 5 is 1. 1 times 3 is 3. 3 minus 4 is -1. So we have our second point that when x equals 4, y equals -1. So let's put those 2 points on there. 0, -4. 1, 2, 3, 4. And when x is 4, y is -1. X is 1, 2, so 1, 2, 3, 4, y is -1. And so now we have a pretty good idea of what the shape of the graph should be. Let me switch colors here. There we go. Okay, got it. And as always, the vertical asymptote and 2 points will shape our graph. And we can check here. Let's just see what that third point would be if we had room to put it in, where we had x equals 24. So we'd have y equals 3 log base 5, 24 plus 1 minus 4, y equals 3. So log base 5 of 25 is 2. We did it that way on purpose. Minus 4. 6 minus 4 is 2. So, way over here, but we can see that it's going in the right general direction, that when we get way over here, it's just going to be, a little bit higher than it is now. So even if we can't fit it on the graph, that'll still give us confidence that it's in generally the right place. So those are the basics of graphing logarithmic functions. And so what we talked about for these couple of more complex ones is start with the vertical asymptote, get that graphed in there. Figure out where, and let me circle here. Figure out where this equals base to the 0 power and where this equals base to the first power. Those are the 2 points that we're going to be interested in and that are going to best help you to shape your graph.